Hello, this is the section 9.2 to 9.3 lesson. In chapter 8 we talked about testing claims about a single population proportion or a single population mean. In this section we're going to look at cases where we are comparing proportions or means from two different populations. So for this lesson you're going to need your calculator. Let's look at this first example. A study was done to determine if echinacea prevents colds. Echinacea is an herbal supplement that's taken for many different reasons. In a study like this, what's often done is that the researchers will give the echinacea or the drug to one group of people, and then to another group of people they'll give what's called a placebo, which is a pill that doesn't do anything. It's like a sugar pill or something that supposedly has no effect, and then they compare the results from those two different groups of people. So 89% of 45 subjects given echinacea developed a cold. So 45 people were given echinacea, out of them 89% developed a cold over some span of time. 85% of 103 subjects given a placebo developed a cold. So 103 people were given this dummy pill and 85% of them developed cold over the same period of time. So what we want to do here is compare these two percentages, 89 and 85. First thing, note that there isn't a whole lot of difference between them. If echinacea did prevent cold, then we would expect that first percentage to be lower than the second one. That's not the case. There's not a whole lot of difference. In fact, the first one is a little bit greater. So based off of this, we might be tempted to say that echinacea does not prevent cold. So let's use this data to test the claim that echinacea has no effect in preventing colds. Well, let's make a couple of quick observations here. First of all, we are comparing proportions from two different populations. Our populations here are first all those given echinacea, and then second all those giving a placebo. Now again, our claim here is about the population of people given echinacea versus the population of people given the placebo. Our data comes from these samples, but we're really comparing proportions from these two different populations. Second point here is that our data comes from two independent samples. First sample is those given echinacea, the second is those given a placebo. They're independent because what happens to one group or one sample has no effect of what happens to the other sample. So our next step is we need to define our parameters. Now we're going to have two parameters in this case because we are comparing two different population proportions. So the claim is that echinacea has no effect in preventing colds. Our first parameter, we'll call it P1, is a proportion of all people given echinacea who developed a cold. And then P2, our second proportion, would be the proportion of all people given a placebo who developed a cold. Again, in both of these we stress the word all because we're making a claim about the population of people given echinacea versus the population of people given a placebo. And we are comparing proportions from those two populations, P1 and P2. So here's our claim: echinacea has no effect in preventing colds. We need to state our hypotheses. Well, if this claim were true, then P1 should be equal to P2, or roughly the same. If it has no effect, then the proportion who took echinacea got cold should be about the same as the proportion given a placebo who got a cold. So P1 equal to P2 is our claim. Well, if that's false, then P1 is not equal to P2. Now our null comes from the one of these two statements that contains equality, which is the first statement. Our null is that P1 equals P2, and our alternative would be the other statement, P1 is not equal to P2. Okay, now these statements look a little bit different than what we saw in chapter 8. Notice that there's no numbers involved here. We simply have P1 and P2, and our null, all of this contains equality. In this case it's P1 equals P2. Our alternative will never contain equality. It will always be an inequality of some sort. Now, we're not going to talk about the formula for the test statistic because it's extremely complicated. We're going to simply let the calculator find the p-value for us. The command here is stat test option 6 2 proportion z-test. It's called a 2 proportion z-test because we are comparing proportions from two different populations, and our test statistic is a z-score, and that's why it's called a z-test. Now our calculator is going to ask for several inputs, x1 and n1, and then x2 and n2. x1 is the number of successes in the first sample, and n1 is the sample size of sample 1. Now, and then x2 would correspond to sample 2. Now x1 and n1 have to correspond to the population that we defined in P1. P1 deals with goes given echinacea, so x1 will be the number of successes in sample 1. A success here again, remember, means simply we observed whatever it is we were interested in. In this case, we were interested in developing a cold, so x1 would be the number of people given echinacea who developed a cold. Likewise, x2 will be the number of people given a placebo who developed a cold. Now in this type of test, it's very important to properly define P1 and P2 so that we can enter our data appropriately. If we switch things around, then our results will come out incorrect. So we first need to calculate x1 and x2. In our first sample, we had 89% that got a cold. We had a sample size of 45, so that comes out to be 40.05. x2, our second sample, we had 85% that got a cold times the sample size of 103, which is 87.55. But remember, we always round off number of successes, so x1 will be 40 and x2 will be 88. These have to be whole numbers. Now enter things in our calculator. You see there in the upper left, option 6, 2 proportion z-test. Below that you see the window where we enter information. x1 is 40, we just calculated that. n1 is 45. And then x2 is 88, we calculated that. n2 is 103. Next we enter the form of our alternative hypothesis, which is that P1 is not equal to P2, so we select that first option. And then below that we either do calculate or draw. We'll do calculate, and when we do that we get a window that looks like this in the upper right hand corner. Notice this says 2 proportion z-test at the top. Below that we have the form of our alternative hypothesis, P1 is not equal to P2. Right below that we have z equals 0.56, that is our test statistic. Below that we have our p-value of 0.57. And then below that it just repeats the data that we entered. It has P1 hat and P2 hat. That's just going to be x1 divided by n1 and x2 divided by n2. Notice that's about 0.89 and 0.85, which agrees with the data that we saw in the original problem. If you scroll down, you'll see more information, n1 and n2. Again, that just to verify that we entered things correctly. The really only important number here is the p-value, 0.57. So 0.57 is our p-value. Compare that to alpha. We'll use 0.05. P-value is definitely greater than alpha, so we do not reject the null hypothesis. So we word the final conclusion the same way. The original claim did contain equality because it's P1 equals P2, so we go to the right. Do you reject it? Answer is no. So there is not sufficient evidence to warrant rejection of the claim that echinacea has no effect in preventing colds. Now this conclusion is a little complicated because we got kind of a double negative. So we do not reject the claim that it has no effect. So what this means in even less technical terms is that echinacea does not appear to prevent colds. Now the requirements for this test are first, proportions are from 2 random samples that are independent. Independent means that what happens in one sample has no effect on the other. And then number 2, for each of the 2 samples, the number of successes is at least 5, number of failures is at least 5. Second one means that we have to have a sample size of at least 10 in order for this test to be appropriate. In our first example, we compared proportions from 2 different populations. In this second example, we're going to compare means from 2 different populations. So a study was done to compare the Weight Watchers and the Atkins diet. 40 people on Weight Watchers lost a mean of 3.0 pounds with a standard deviation of 4.9 pounds. And 40 people on Atkins lost a mean of 2.1 pounds with a standard deviation of 4.8 pounds. Now if we just look at these numbers here, notice that the mean weight loss for Weight Watchers was quite a bit larger than the mean weight loss for Atkins. That's an indication that maybe Weight Watchers is a little bit better diet. But another thing we want to observe is the standard deviations. Notice that these are very large, 4.9 and 4.8. So that means our data are very spread out. What that means is that we have some people who maybe lost a lot of weight, some people who lost not very much weight. We maybe even had some people who gained weight, meaning a negative weight loss. Okay? But if we just compare those means of 3 and 2.1, we might be tempted to claim that the mean weight loss on Weight Watchers is greater than the mean weight loss on Atkins. The data appears to support that claim, and so let's use it to formally test it. Make a couple of observations here. First of all, we are comparing the means from two populations, all those on Weight Watchers and all those on the Atkins diet. Those are our two populations. Our data comes from two independent samples. We have the 40 people who took Weight Watchers, that's our first sample, and then the 40 people who took Atkins, that's our second sample. They're independent because what happens to one sample has no effect on what happens to the other. Now we need to define our parameters. We have two parameters in this case, just like in the first example, but here we have mu1 and mu2 because it's a claim about means. So mu1 would be the mean weight loss for all people on Weight Watchers. Mu2 would be the mean weight loss for all people on Atkins. Again, we stress the word all there because we're making a claim about the populations of people on Weight Watchers and population of people on Atkins, not just our samples of 40 people each. State our hypotheses. The claim in mathematical notation would be that mu1 is greater than mu2 because the claim is that the mean for Weight Watchers is greater than the mean for Atkins. Now if false, mu1 is less than mu2, our null comes from the one of those two that contains equality, mu1 equals mu2, the alternative is the other one. So notice that these hypotheses look very similar to example 1, except that we're using mu instead of p. Again, the formula for our test statistic is very complicated. We're not going to talk about it. We'll use our calculator to find the p-value. So the option here is number 4, two-sample t-test. Two-sample means that our data comes from two independent samples, called a t-test because our test statistic is indeed a t-score. Now it's going to ask for x bar 1 and 2, which are our two-sample means, sx 1 and 2, which is our sample standard deviations, and then n1 and n2, which is our two sample sizes. So once you choose that two-sample t-test, you'll get a window that looks like this on the upper left. We have two options for inputting our data. If we have the data, raw data, we can enter in a list and choose that first option. That's not what we have there. We have summary statistics from our two samples. So we'll choose that second one. And there you see we enter x1 bar, sx1, n1. Again, those are all going to correspond to the sample that corresponds to mu1. Which because the Weight Watchers diet. So x bar 1 is 3, sx1 is 4.9, n1 is 40. And then below that we have x bar 2, sx2, and then you scroll down, we enter sx, and then n2, sorry. Again, that's going to correspond to the Atkins. Below that, we enter the form of our alternative hypothesis, which is mu1 is greater than mu2. So highlight that and select it. And then it asks for pooled, either yes or no. All of us choose no. We won't go into what that means, we just always choose no. Now if you hit calculate, you'll get a window that resembles this in the upper right hand corner. It gives us a lot of information. The first, mu1 greater than mu2, which is our alternative hypothesis. Next it gives us our test statistic t. Right below that is the p-value, which is the only important output. And then below that it gets df, which is degrees of freedom, and then it repeats our summary data that we entered before. We can scroll down to see the other numbers that we inputted, just to verify that we entered things correctly. Again, the important thing there is the p-value, 0.204. And now we come to our technical conclusion the same way. That's greater than 0.05, which is alpha, so we do not reject the null hypothesis. Word the final conclusion the same way. The original claim does not contain equality because its mu1 is greater than mu2. Do you reject it? No, we do not. So there is not sufficient sample evidence to support the claim that the mean weight loss on Weight Watchers is greater than the mean weight loss on Atkins. So our data did appear to support the claim, but that level of support was not strong enough. So what this means in even less technical terms is that there does not appear to be a significant difference between the two diets. Now let's just make a quick observation here. We noted that in our original data we had very large standard deviations. Let's change those standard deviations to a smaller number and just see what happens. So let's change both those standard deviations to 2 and recalculate the p-value. Let's keep our sample sizes and our sample means the same. So there in the left window you see how we've entered SX1 to be 2 and SX2 to also be 2. Everything else is the same. On the right you see the result. P is 0.0238. So there's our p-value. Now in this case this is less than 0.05, and so we reject the null hypothesis. That's the opposite technical conclusion. Word the final conclusion. We go, original claim does not contain equality, no. But in this case we do reject the null hypothesis. So our final conclusion would be that the sample data support the claim that the mean weight loss on Weight Watchers is greater than the mean weight loss on Atkins diet. So if we have these smaller standard deviations, we come to the exact opposite final conclusion. Large standard deviations, the data did not support the claim, but with smaller standard deviations, they do support the claim. So the point is that we must be careful about comparing means from samples with large standard deviations. If we have large standard deviations, then simply comparing the means, we got to be real careful about that. We may get opposite results of what we expect. Now the requirements for this type of test where we're comparing two means is that the two samples are independent, again meaning that what happens to one sample has no effect on the other. Second, both samples are random. And then number 3, either of these conditions is satisfied, either both sample sizes are greater than 30, or both samples come from populations having normal distributions. Now this third requirement looks very similar to the requirement for the central limit theorem, and that's because the central limit theorem forms the theoretical foundation for this type of a test. That's it for this section. The homework is section 9.2 to 9.3.